Hi everyone, good morning. Let's start our exercise class. So in this exercise class, I'll have the following plan. So first I'll discuss the connection of density matrices for a qubit to the Bloch sphere. Then we'll look at how we can distinguish the states given by density matrices and why sometimes it can be less trivial than it seems. And finally, we'll just repeat what we learned from the lecture about the Kraus operators and Stinespring dilation, and also look at the example of how we can find Kraus operators for a particular quantum channel. Okay, so let's start with the density matrices. And the Bloch sphere. So the idea is here is that we know that for geometry of the set of states, we have, especially for the states of the qubit, which is like the most prominent example of such representation, we can graphically see the states of the system as just the points on the three-dimensional sphere, which is called the Bloch sphere. But the problem is that geometry of the set of density matrices is not as simple as the geometry of the state spaces. So essentially pure quantum states, so the states which we can just write, for which the density matrix we can just write as psi here. So for this states, kind of psi are points on Bloch sphere. We've looked at it at our previous considerations. So we have a sphere with the radius 1, and then each state of the qubit can be seen as just a point on the sphere. Okay. We also, like, if you ever taken a probability theory course, you would also know that the probability distributions form a simplex. So it's just a generalization of a triangle, but it doesn't matter. So what I want to say is that for the pure quantum states, we have some representation, and for a probability distribution, we also have some geometric representation. But in an arbitrary case, for an arbitrary dimensional system, it is not at all simple. It is not at all simple to formulate what exactly is the geometry of the set of the density matrices. However, there is an elegant and simple representation of this geometry for the case of the qubit. So for the case of the dimension equaling 2. And now we will show how we can come to this representation. So suppose that we are given a Hermitian matrix or 2 by 2, which we call A. Then the first step that we have to make, we have to actually see that we can, for any Hermitian matrix 2 by 2, we can express it in terms of the Pauli matrices and the identity matrix. So we can express A in terms of the Pauli matrices plus the identity. Why? Because actually the set of the Pauli matrices, which we will here label as sigma x, sigma y, and sigma z, plus the identity, form a basis for 2 by 2 Hermitian matrices. So I will not show this explicitly, but one can easily show it by first showing that these four matrices are linearly independent. So essentially, let me see, to show. So first, sigma x, sigma y, sigma z, and the identity are linearly independent. Okay, so that is easy to show. So in a way, you should suppose that, okay, suppose that they're not linearly independent, then there exist like non-zero coefficients C1, C2, C3, C4, such that C1 sigma x, and yeah, so these are just coefficients, C1 sigma x plus C2 sigma y plus C3 sigma z plus C4 identity equals 0. And from this, just writing out the Pauli matrices as they are. So maybe again to remind you, sigma x looks like this. Sigma y is this matrix. Sigma z is this matrix. So this are the Pauli matrices which we already seen before, and the identity is just the identity. And from this, from this assumption that they are not linearly independent, what we get is that all these four coefficients equal 0, which means that they are linearly independent. And the second thing that we have to show is that every Hermitian matrix can be written as a superposition, as a linear superposition of these four matrices. And this is kind of intuitively easy to see because so if we take any matrix 2 by 2, then essentially the number of the free parameters for such a matrix is 8, because we have 4 entries in the matrix, and each entry can be is a complex number which adds 2 parameters. So we have 4 entries, each entry has 2 free parameters, so that would be 8 entries. So for an arbitrary matrix 2 by 2, we have kind of this 8 free parameters. However, for the Hermitian matrix, we also have a condition that it has to be equal to its own conjugate transpose, which gives us 4 more, which gives us 4 conditions on these 8 parameters, 8 free parameters, which leaves us with only 4 free parameters. So essentially, for the Hermitian matrix, we have 4 free parameters, and hence, in the end, the basis that that would have to describe this this basis that would have to describe this Hermitian matrix would need to have 4 elements, because we need to have 4 free parameters. And hence, since we prove we've taken this basis of sigma x, sigma y, sigma z, and identity, and we can show that all these 4 basis elements are linearly independent, then hence we can arrive to the conclusion that indeed these are the 4 possible basis elements that we can choose to describe a Hermitian matrix. Okay, so now let us, since now we know that we can write this Hermitian matrix in terms of Pauli matrices and the identity, let us write it out in the following way, with the following coefficients. So A01 plus A1 sigma x plus A2 sigma y plus A3 sigma z over 2. So I'm choosing the coefficients as A0 over 2, A1 over 2, A2 over 2, and A3 over 2. Just for convenience, we're going to see in a moment why this matters. So the next condition comes from the conditions that we put on the density matrices. So we know that for the density matrix, the trace of the density matrix has to be 1. Okay, so from this condition, we come to, so the trace of A would be equal to just A0 over 2 trace of identity plus A1 over 2 trace sigma x plus A2 over 2 trace sigma y plus A3 over 2 trace sigma z. And actually, if you look at the Pauli matrices here, sigma x, sigma y, and sigma z, they all have traces 0. So essentially, this is 0, this is 0, this is 0. And we are only left with a trace of identity. And hence, it's A0 over 2 by 2, which is A0. So from this, it follows that A0 equals 1. Okay, let us substitute this in our equation. So what we get is identity plus A1 sigma x plus A2 sigma y plus A3 sigma z over 2. Now let us introduce two vectors. So the first vector would be just a vector which we call A. And this is the vector of 3 coefficients that we have in our basis decomposition, A1, A2, and A3. And the second vector would be vector sigma, which will be the vector of the Pauli matrices. Be sigma x, sigma y, and sigma z. And this notation allows us to write out the matrix A in a compact way. So A equals then identity plus the scalar product between vectors A and sigma over 2. Okay, so we arrive to this representation of the matrix A. There are some things which we still haven't taken into consideration. So another property of the density matrix that the density matrix has to satisfy is that it has to be positive semi-definite matrix. And we will use this property of A to find the condition on the vector A. We need to use that A, if it is indeed a density matrix, has to be positive semi-definite. So what does it mean for the matrix to be positive semi-definite? So it has to satisfy the property that all of its eigenvalues have to be equal or greater than 0. So the eigenvalues of A has to be greater or equal to 0. Okay, then let us find this eigenvalues. For this, let us write the matrix A just in the matrix form. So what we have is like 1/2 of the identity plus A1 by sigma x, which will be this, plus A2 by sigma y, plus A3 by sigma Z. Okay, what we arrived to, sorry, and here, of course, all 1/2 because of the half here. Then we arrive to that this is equal to the matrix 1/2, 1 plus A3, A1 minus IA2, A1 plus IA2, and 1 minus A3. To find the eigenvalues, we need to write the characteristic equation for them, which in this case, so we call the eigenvalues lambda as usual. So in this case, it would just be 1 plus A3 minus lambda, 1 minus A3 minus lambda, minus A1 minus IA2, A1 plus IA2, and this has to be equal to 0. Let us open some of the brackets. Here we get 1 minus lambda squared minus A3 squared, minus, here we get A1 squared plus A2 squared, and this would be equal 0. Okay, we can massage this equation further. What we get is 1 minus lambda squared would be equal to A1 squared plus A2 squared plus A3 squared. Which if we remember that we can write, we already introduced the vector A, this would be just the modulus of vector A squared. Vector A is just the vector which has the components A1, A2, and A3. And from this, we can conclude that lambda is equal to 1 plus minus modulus A. And for A to be positive semi-definite, this is equivalent to lambdas being positive or equal to 0. And this is the same as saying that modulus A is less or equal than 1. Because we want 1 minus modulus A to be bigger than 0, then modulus A is less or equal than 1. So this is the final condition which we found on the vector A. So, so to summarize our findings, we found that the set of two-dimensional density matrices is precisely equal to the set identity plus A by sigma over 2, such that the modulus of vector A is no greater than 1. Okay, so what we found here is actually that the set of matrices can be only characterized by this vector A. So the length of the vector A is no bigger than 1, which means that geometrically, this can be represented as a unit ball in 3 dimensions, in R3. Let me draw a picture. So here we have our 3 dimensions. Then sorry, this is not, okay. This is fine. So we have this ball in 3 dimensions, let's say X, Y, Z. And then essentially the idea is that all the points inside the ball, including the points on the surface, they correspond to, they can be mapped to a particular density matrix. So if you choose a point inside a ball or on the surface somewhere here, and it will be characterized by this vector A, and for each vector A we have its own density matrix, which can be found using this mapping. So let us look at some examples. So the first example, suppose that we're looking at the pure state. Let's take the state 0. So rho is 0, 0. Yeah, just in the matrix form, this will be 1, 0, 0. So let us do here an explicit calculation to what vector A of this density matrix corresponds to. So we need to find A such that this would be equal to 1, 0, 0, 0. So we already kind of expressed like this, expressed this 1 plus identity plus A by sigma over 2 in terms of the matrix, which we found here. And so we just need to find A1, A2, and A3 such that the matrix would be equal to the matrix 1, 0, 0, 0. So let us just rewrite what we had on a previous slide. So previous page. This would be so, and here the solution is quite obvious. So if we take A1 equal A2 equal 0 and A3 equal 1, then we precisely get the density matrix of the state 0, 0. And hence, if we take this density matrix, it corresponds to the vector A, which is 0, 0, 1. Let us draw it on the picture. Use the red pen. So this would be this vector A, and hence this would be the state 0, 0. So if you look at all the pure states, then all the pure states form the surface of the ball. Yeah, so if you take any pure state, then and if you try to find this its representation on the Bloch sphere, like it's similar to the Bloch. It's exactly similar to the surface of the Bloch sphere that we discussed before for the pure states of the qubits. You find the state on the surface of the ball. Like another extremal case is when we take the maximally mixed state. So maximally mixed state for the qubit, this would correspond to the state where you would prepare the state 0 with probability 1/2, and you would prepare the state 1 with probability 1/2. And this corresponds to the density matrix 1/2, 0, 0 plus 1/2, 1, 1. And this is just 1/2 of identity, right? And we need to find again the vector A such that this 1/2 of identity is equal to 1/2 of identity plus sigma by A over 2. And again, trivially, the solution is A equals 0. So it's a 0 vector, which means that the maximally mixed state corresponds to kind of the center of the ball. So if we have our ball, then actually the maximally mixed state lies right in the center. So this is maximally mixed state. And so already intuitively, you can see that kind of the idea of how pure the state is also relates to the idea how close it is to the surface. So we have on the surface of the Bloch ball, we have only pure states. And then in the middle of the ball, we have, in the center of the ball, we have a maximally mixed state. And then going from the center to the surface, we gradually have like states which are kind of pure and pure. Okay, so this was about how we can represent the two-dimensional, the density matrices for two-dimensional systems geometrically. So this kind of geometrical representation works only for for two-dimensional systems. For an arbitrary dimension, this is not so nice. Like it's not it's not even clear for an arbitrary dimension how the set of the density matrices is geometrically, but for this case of the qubit, this is quite elegant and simple, and this kind of representation can be used to like understand to get an understanding so how pure the state is. Okay. There was something. So there is a question in the chat. Do they span only the space? Oh, no, probably a long time ago. Sorry, I only saw the question now. So I guess like the question is, do they span only the space of Hermitian matrices or all matrices of dimension d equal 1? Or sorry, d equal 2? So you mean the Pauli matrices, right? Okay. Let me think for a moment. So okay, so if we choose the elements of the my answer would be no, because for an arbitrary 2x2 matrix, as I said, we need 8 free parameters, and if we choose the set of Pauli matrices and in the decomposition allow only for the like rational coefficients, then the only matrices that we would be able to get would be Hermitian matrices, because all Pauli matrices are Hermitian and the identity is also Hermitian. And so if we combine them with only coefficients which are real, then we only get the a Hermitian matrix. If we allow for the complex coefficients, then I think yes, they do form a basis for all 2x2 matrices. Okay. So now let us proceed to the next point, which is about distinguishing the states and why this can be a bit more difficult when we're dealing with density matrices. So let us first look at the one-dimensional system, and then we'll go to the two-dimensional case. So first we only look at the single system, single qubit, what I meant, and then we will go to the case when we have a joint system of two qubits together. So precisely going from two-dimensional systems to four-dimensional. Okay, so now how we can, now the idea is that how if we are given two quantum systems which are in two different states, and we are said that it's either in the first state or in the second, how can we distinguish these two situations? And the only way we can do so is, of course, by measuring the system and looking at the probability and looking at the, essentially in the end, at the probability distribution of the different outcomes that we get. So measure plus probability distribution. So the case of one qubit. Suppose that we take, we're given the system, and we know that it is in one of the states. The first state is just the pure state plus plus, where plus is 1 over square root of 2, 0 plus 1. And here we have the bra. So this is the first state, which is just 1/2. I'll write this in terms of the matrix. 1, 1. Okay. And the second system, and the second version of the state, which we call rho A prime, would be the maximally mixed state. 1/2, 0, 0 plus 1/2, 1, 1. In the matrix form, this would look like 1/2 identity matrix. Okay. Now let us first do a naive attempt to measure these states in 0, 1 basis and see if there is a difference in probability distribution. So in the end, are we able to distinguish the states by just measuring in 0, 1 basis and saying that they would just yield different different probability distributions for the outcome 0 and 1. So attempt to measure in 0, 1 basis. So for the first state, which is rho A, the probability of measuring it, the system in the state 0 can be written as just this. So just rho A squeeze between the brackets of the 0 state. And let us do this in a matrix form. So the bra 0 state can be written as just the matrix 1 by 2, 1, 0. Then rho A is 1/2, 1/2, 1/2, 1/2. And ket 0 is just the column 1, 0. Right, we can calculate this. What we get is, from the first multiplication, we get 1/2, 1/2. Multiplying it by 1, 0, we get 1/2. Analogously, the probability of getting the outcome 1 would be also 1/2. Fine, so this was for row A. Now let us look at the similar thing, but for row A prime. Then the probability of getting outcome 0 would be just 0, row A prime, 0. Okay, this would be equal to, again, 1, 0. A different matrix now, which corresponds to row A prime, 1/2, 1/2, column 1, 0. Here we get 1/2, 0, 1, 0, 1/2. And analogously, the probability, let me call this probability as prime, p prime of 0, p prime of 1, would be also 1/2, which means that if we measure these the system and the 0, 1 basis, then we will actually never be able to distinguish whether it's the state row A or whether it's the state row A prime, because essentially for the measurement in 0, 1 basis, they yield the same probability distribution. So this is kind of hopeless, but let's not give up. So the second thing we can do, we can choose some other bases to measure these systems in. So let us measure in plus minus basis. So just to remind again, plus is 1 over square root of 2, 0, minus 1, and minus, oh, sorry, plus 1 here, and minus is 1 over square root of 2, 0, plus, I don't know what's pluses, what was with pluses and minuses today, but so minus is just 1 over square root of 2, 0, minus 1. Okay. So now we measure in this basis. And again, we separate our predictions for row A and row A prime. And first we calculate for row A. So what is the probability here of getting plus? This is kind of easy because we know that actually if we look at the row A, it's a pure state, which is exactly so it's a state which is prepared in a state plus with probability 1, which means that if we measure plus, then we measure it with probability 1 because we've prepared it in the state plus with probability 1. And hence the probability to measure the system in the state minus is actually 0. Now come to the second case. So what is the probability of measuring the system row A prime, which is just this system, in the state plus? Well, here we have to do the calculation. So we have plus row A prime plus. Then plus is just the row vector, 1 over square root of 2, 1 over square root of 2. Row A prime is 1/2, 0, 0, 1/2. And the ket plus is just the column vector, 1 over square root of 2, 1 over square root of 2. Okay, we calculate again. So I'll take 1 over square root of 2 out and 1/2 also out. Then what we get here is 1/4, 1, 1, 1, 0, 0, 1, 1, 1. And here we just calculate. So what we get here is 1, 1 by 1, 1. We get 1/2. And analogously, the probability of measuring minus would be also 1/2. Okay, so we found a measurement which allows us to kind of yield different results for different states for the two density matrices, rho A and rho A prime. So if we measure the system in the basis plus minus, then in the case that the system is in the state rho A, then we would always get the result plus. However, if we measure the system, if we measure the system in the plus minus basis and we get like sometimes plus and sometimes minus, like with the same frequency, then essentially what that means is that actually the system is in the state rho A prime. So if the system was in the state rho A, we would never get minus. If the system is in the state rho A prime, we will get minus as often as plus. I feel like the screen has frozen. Let me. Yeah, okay, now it's good. So now we can distinguish states rho A and rho A prime. So as you see here, the devil is kind of in the detail of choosing the bases. So we need to choose the bases carefully to be able to distinguish two states. Okay, so now let us proceed to the case of two qubits, which is also the case of the problem in the exercise sheet. So we have two qubits. Let's label them A and B. And the joint system is the Hilbert space, the tensor product of their Hilbert spaces of A and B. And we'll be looking at three states that we would need to find a way to distinguish. So the first state, we call it rho AB. It's a pure state, which we write as psi1 AB, where psi1 AB is one of the Bell states. 1 over square root of 2, 0, 0 plus 1, 1. We already seen these Bell states when we were looking at the teleportation protocol. And just to write this in the matrix form, so as we remember, the density matrices on 2-qubit systems, they correspond to 4x4 matrices. So we can just write this matrix based on the states of psi1. Okay, so this is the first state. Then the second state, which we call rho AB prime, which would be the mixed state, 1/2 0, 0 plus 1/2 1, 1. So again, the interpretation of this state is that we prepare the two systems A and B in the state 0, 0 with probability 1/2, and in the state 1, 1 with probability 1/2. This corresponds to the matrix 1/2 0, 0s this because we only have components 0, 0, 0, 0, and 1, 1, 1, 1. And finally, the last state that we consider is, we call it row AB double prime. And it is just the tensor product of the maximally mixed states on each qubit. So it's 1/2 identity on A, tensor product 1/2 identity on B. And this would give us just 1/4 of the identity matrix on both systems. So we have this three possible states, and then we need to find a way to distinguish them, which means that we need to find some measurements on the systems A and B, or on the joint system of A and B, such that for each of these states, these measurements would yield different probability distributions. So why is this why this can be problematic here? So imagine the situation as follows. So there are two agents, Alice and Bob. Each one of them has access to systems A or B. Like Alice has access to system A, and Bob has access to system B. And then they want to together somehow distinguish between these three states. So they want to find out which state they have in their labs. And the first question is, well, can each one of them do it individually? So can Alice distinguish between these three states that she has to with Bob, only performing local measurements on her system A that she has in her lab? So can this be done by just local operations? So local operations here mean that the operations only on system A, or the operations only on system B. And here this also means that A and B cannot communicate their results to each other. So actually this cannot be done. So why? So for us to understand how the system looks like in A's lab, or essentially to which system A applies her local operations, if she doesn't communicate with Bob. This is exactly the kind of the reduced state. So Alice is working with the reduced state of the system A in her lab. And so let us calculate the reduced states of A. So these are the states to which she would ultimately apply the local operations that she does in her lab. And this reduced state would also give us the result of the probability distributions of the measurements that she performs in her lab. And to find out whether actually the state, if the state looks differently in Alice's lab for these three cases, so we need to calculate the partial trace of the matrices row AB prime, and row AB double prime, tracing out the system B. So if we take the first case of the state row AB and trace out the second system. So we are tracing out the second system from the state, which is here. I'll write it in a bracket notation. So this was the pure state, psi 1, where psi 1 is 0, 0 plus 1, 1, and normalization 1 over square root of 2. And I write this in bracket notation. And here, let us do this process of taking partial trace explicitly. So we need to sum over the basis states of the system B, multiplied by a tensor product, or just acting an identity on the system A. So what we get is, I take out 1/2, which comes from 1 over square root of 2 squared. And the first component in the sum would be 1 on A, 0 on B. Sorry, identity on A, 0 on B. Here we have 0, 0 plus 1, 1, 0, 0 plus 1, 1. And from this side, the same thing, identity on A, 0 on B, plus the same term, but acting with the basis state 1 on B. So we would have, sorry, there was a bug in my, there is still a bug on the ceiling, but sorry. So the second term is just 1A, identity on A, 1 on B, 0, 0 plus 1, 1, 0, 0 plus 1, 1, identity on A, 1 on B. And I will not open all the brackets and see which terms in this expression die out, because yeah, I guess we already did it last time, and it's a lengthy process. And actually one can see it quite easy, which terms die and which don't, because here we have 0, here we have 0. So essentially all the terms which have 1 in bra or in ket on the second system B. So for example, this or this, they die out, all the terms which have these expressions in. So then the only term that survives would be this. And in the second term in the expression, it will be this. So it's only 2 terms that survive. Then what we get is 1/2, 0, 0, A plus 1/2, 0, 0, B. If this is not clear, you still can open all the brackets and do it the lengthy way. But what I'm claiming here is that it's only these 2 terms that will survive. Okay, so then let us look at the row A prime. So what is the reduced state of the system A? If the initial state of both systems is row AB prime. So here we just trace out the second system. Where the initial state of the system is just this mixed state. The states 0, 0, and 1, 1. And I will, essentially, you have to do the same calculation as before, just doing the partial trace. I claim that this would give us the same state as before. Oh, sorry, this should be A. And this should be 1s. Okay. And finally, if the system if the joint system is initially in the state rho AB double prime, then the reduced state of the system A, tracing out system B. Here it's the easiest because here the density matrix of the joint system just separates into density matrices on the individual subsystems, and hence like the reduced density matrix of the system A would just be the density matrix 1/2 identity, which is also this 1/2 0 0 plus 1/2 1 1. So we have analyzed what happens if it's only Alice who does some local measurement on her side, some local operation on her side, and the question is whether she's able to find kind of the difference just between these three states, just doing this local measurement on her side. And since the probability distribution for the local measurements on her side would be given by the reduced matrix on her system A, then we compared all these three reduced matrices for all three cases, and we saw that actually for all three cases, the reduced density matrix on the system A is the same. Which means that no matter which operation she does locally, there is no way for her to, on her own, just to distinguish these three states. So no way to distinguish by Alice doing local measurements on her own. The same holds to Bob because, as you've seen, all the states that all these three states, they're symmetric with respect to Bob and Alice. Yeah, so same holds for Bob. But let's not lose the hope yet. What they can do. So what we can do in this case. There are two things that we can do. So first is for Alice and Bob to make measurements, to make local measurements, each on their own side, and then communicate the results to each other. And then together they will be able to decide which state they have, which joint state they have. So this is local measurements plus classical communication. So first they do the measurements in their labs, and then so on the systems that they have access to, Alice does a measurement of the system A, Bob does a measurement on the system B, and then they communicate the results, and based on like their joint result, these two results, then they can judge which state it was. And we will look at different cases. So the first case, so Alice and Bob measure in 0, 1 basis or plus minus basis. Here the same, and communicate the result. And decide which state they have. And the second is, which is a bit harder, if Alice and Bob's labs are somehow separated and they share the state. which is far while being far away from each other. But if they're, for example, in the same lab, then they can also do a global measurement of the system, of the joint systems of A and B in Bell basis. So the Bell basis, just to remind you, you already seen it in the teleportation protocol. So this is just 4 states which form a basis of 2-qubit system, so for a 4-dimensional system. So this would be 1 over square root of 2, 0, 0 plus 1, 1. Psi 2, 1 over square root of 2, 0, 0 minus 1, 1. Psi 3, 1 over square root of 2, 0, 1 plus 1, 0. And psi 4, 1 over square root of 2, 0, 1 minus 1, 0. So this is just the Bell basis. And to illustrate how this measurement, communication, and like then finding out, final distinguishing of these 3 states happens, we can look at the following table. So in the columns of the table would be the method that we're using, and in the rows will be the states. So here we have row AB prime, row AB double prime. Then first, the first way for Alice and Bob to distinguish the states is to, if they both measure in 0, 1 basis, and then communicate the result. So measuring in 0, 1 basis would be equal to just measuring this operator Z. But it just means that Alice measures in 0, 1 basis, Bob measures in 0, 1 basis, and then they compare the results. Second way for them to distinguish is if each one of them measures the state in plus minus basis and then compares the result. So measuring plus minus basis is the same as measuring the operator X. So so Alice and Bob both measure the operator X on their individual subsystem. But this just means that they measure in plus minus basis. Bob measures in plus minus basis, and they share the results. And finally, there is a joint measurement in Bell basis. So, okay, so we have 3 methods. We just need to see like how and when each method works. And like I claim that the result will be the following. So if they both measure in 0, 1 basis, then the only results that they can get in case it's the system is in the state row AB is either 0, 0 or 1, 1. So we label the result as 0 if we get if we measure the state 0, and we label the result 1 if we measure the state 1. So it would be the same for row AB prime, but for row AB double prime, they actually can get any combination. 0, 1, or 1, 0, or 1, 1. So each one of these combinations of their measurement outcomes has a non-zero probability to occur. In the case where they measure in plus minus basis, then here and here, for the first 2 states, row AB and row AB prime, they could both get, they could get either plus plus or minus minus. So these two cases are the same, so you can't really distinguish it. Rho AB and rho B prime, the same as when they measured in 0, 1. However, for rho AB double prime, they again can get any combination of plus and minus. And finally, for the Bell basis, if they make a measurement in a Bell basis, if they measure rho AB, obviously, I mean this part of the table is obvious that they get they would only be able to get the measurement outcome psi1 because rho AB is the pure state. So it was prepared in a state psi1 with a probability 1. For the rho AB prime, the only two measurement results that they can get is psi1 or psi2. And for rho AB double prime, it's either, they can get any of the 4. So the global measurement allows them to actually distinguish between all of these 3 states. So I'll just do here the example of the calculation for rho AB, how we calculate the results in the first row of the table. So to remind, rho AB is just the pure state psi1 in the matrix form, can be written as this. Okay, so then the first entry in the table, what is the probability of Alice and Bob both getting outcome 0 if they measure in the 0, 1 basis? And this is just 0, 0, rho AB, 0, 0. Using the matrix form, the 0, 0 bra is just the row vector 1, 3 zeros. Then here we have rho AB. And here we have the column vector 1 and 3 zeros. So if we calculate this, this would give us 1/2. Same for the probability of them both getting outcomes 1. It would also be 1/2. So maybe I write it just for this time in the matrix form as well. So it would be 0, 0, 1, 1/2. So it would be 1/2. And the probabilities, and because we already have like that the probability of 0, 0 is 1/2 and probability of 1, 1 is 1/2, there is no room left for the cases 1, 0 and 0, 1. So the probability of this is 0. So essentially, if we have the state rho AB and we measure in the basis 0, 1, then then we get the outcomes 0, 0 or 1, 1 with probability 1/2 each. Okay, now let us consider the second. So we just shown this entry of the table. Now let us consider the next entry. So what happens if we measure rho AB in plus minus basis if Alice and Bob each measure their own subsystem in plus minus basis? Okay, so we need to calculate the probability of them both getting outcome plus. So it would be plus plus AB, rho AB, plus plus AB. So what is plus plus AB in the matrix form? This is just plus on A, tensor product plus on B. this is just the vector 1 over square root of 2, 1 over square root of 2, tensor product 1 over square root of 2, 1 over square root of 2. This is 1/2. We get the vector 4 by 1, 1, 1, 1, 1. Okay, then let us continue with calculating the probability of them both getting outcome plus. Here we get 1/2, 1, 1, 1, 1 in a row. Then our matrix. And here we get them in a column. So we get here 1/8 by, so here we get 2, 0, 0, 2, 1, 1, 1, 1. So 1/8 by 4, 1/2. Okay, analogously, probability of them both getting minus, which would be minus minus AB, row AB, minus minus AB, would be equal to also 1/2. You can calculate it in the same way. And hence the probabilities of minus plus and plus minus would be 0. So if we have the state row AB and Alice and Bob each measure the systems A and B in a plus minus basis, then they can both get plus with probability 1/2 or both get minus with probability 1/2. These are the only two options. So we've just shown this entry in the table. And the last entry for this row, for the state row AB, is on this entry, that if you measure in a Bell basis the state row in B, you can only get outcome psi1, which is trivial, as I said, because already the state row AB is the state of psi1, which is prepared with a probability 1. So we can only get the outcome psi1. So we've shown this row for what happens if A and B either do local measurements in their labs and then communicate the result, or they do a joint measurement on both systems. And we did an analysis for row AB. The same analysis can be done for row AB prime and row AB double prime. And the entries of the table can be shown in a similar fashion. Maybe to again repeat. So if A and B do the measurements, local measurements, and then communicate, then coming from these entries, these 4 entries here, you see that A and B cannot actually distinguish between the states, between the states row AB and row AB prime, because the probability distribution for the results would be the same. However, they can distinguish for the state row AB double prime. And also, if they do the global measurement on the joint state, then they're always able to distinguish between these 3 states, because for all 3 states they would have different probability distributions. And probability distributions of the measurement results. Okay, and so the last thing for today is the Kraus operators and Stinespring dilation. And here I'll just outline the concept. I will not go into like the proof or the derivation of why the Kraus operators, this operator sum representation holds, or why this Stinespring dilation always holds. So I'll just try to recap the concept. So the concept is that when we first started postulating the quantum mechanics, the rules of quantum mechanics, we said that, oh, the system is represented by a state in Hilbert space, and the time evolution of the state is given by some unitary operator U. And this is the postulate of the quantum mechanics, and we've chosen the unitary operator because we needed the map to be linear, essentially. And but now, since we have this description in terms of the density operators, the density matrices, the question is, what is the general evolution for the density matrix? If we consider the density matrices. Of course, so essentially we're looking for the maps which would map density operators to density operators, and which would be linear, and also preserve the properties of the density operators. And the question is, how can we characterize all such maps? So we know that, so one type of the map is, of course, if we just take the density operator and apply a unitary and map it to rho prime, which is U rho U dagger. So this corresponds to a unitary evolution. And this would map pure states to pure states. But what if we want to map a pure state to a mixed state? For this, we need a quantum channel, like an object which is generally called a quantum channel. So rho maps to some rho prime. We usually write channels as epsilon of rho. And one can show that under certain assumptions for these channels, one can represent these channels as sum over k, ek rho, ek dagger, with operators ek such that sum ek dagger ek over k would be identity. So this is called an operator sum representation. And EKs are called Kraus operators. So this can be, again, I will not derive it here, but this can be derived from following assumptions. So we assume that the quantum channel has to be linear. It has to be trace preserving because we need to map density matrices to density matrices, and the trace of density matrix is always 1. And it also has to preserve the positivity. So it has to map the positive, the positive semi-definite matrices to positive semi-definite matrices. Again, because this is a condition we have for the density matrices. So out of these 3 conditions, you can actually derive that the map would look as follows. And these maps are also called CP TP maps, which means completely positive trace preserving maps. So, and one final, maybe one final thing I wanna note about the quantum channels, which is also connected to the Stinespring dilation, is what is the interpretation of the quantum channel? So why are there these channels which map like from pure states to the mixed states and back? Because the intuition would be that, okay, in the postulates of quantum mechanics, we had this postulate of unitary evolution. So everything should evolve unitary, and unitary evolution also means that the energy is conserved, and so on. But here we have some kind of evolution which does not necessarily preserve energy, which maps some pure states to the states which cannot be described in terms of pure states, but rather in terms of, oh, this is a description of me preparing the state, and 0 with probability 1/2 and 1 in probability with probability 1/2 and so on. So how do we explain this while still kind of retaining the unitarity of the bigger process or the processes which happen? And this can be interpreted as having the system A to which the channel is applied, but also having a second system, which is the environment. And the idea is that if we consider both systems to which the channel is applied, and also the environment system, then one can show that one can always find such an environment system and such a unitary process, such that the channel applied to the system A would correspond to applying some unitary process to the environment and the system jointly, and then just tracing out the system, then just tracing out the environment. So essentially, then this just corresponds to the channel epsilon, and then in the end, what you get here is epsilon of rho A. So epsilon of rho A is, first we apply a unitary to the joint system of A in environment, and then we trace out the environment. Yeah, and this allows us to still see the processes, the bigger processes that happen as unitary processes, because then you can say that, okay, so I have this quantum channel which does not really preserve the purity of my state, but what this actually means is that some bigger unitary process happened on a bigger system, including the environment, and then the environment was just traced out. So the system A is kind of is the open system to which is the part of a bigger system which is closed, to which the unitary evolution is applied. And yeah, this is a very like good and intuitive way to think about what happens to systems when they're subjected to some quantum channel. Yeah, and yeah, Lydia told me that in the lecture you've seen some examples of the quantum channels, and in the exercise class in the exercise sheet you would also need to find Kraus operators for a depolarizing channel, and maybe I'll just give you one hint. So the depolarizing channel is the channel that maps rho to rho prime, which is 1 minus p rho plus p identity over 2. And you need to find the Kraus operators for this channel. This is pretty easy if you use the following trick. You need to represent the identity. You need to show that the identity can be represented as 1/2 rho plus sigma x rho sigma x plus sigma y rho sigma y plus sigma z rho sigma z. And for this, so to show this, use a Bloch ball representation that we just discussed in the beginning of the exercise class. And then if you insert the identity here instead of the identity in the channel, then you'll immediately see to which Kraus operators this channel corresponds. So then rho prime, which is epsilon of rho, would be just like E1, was it? Yeah, E1 rho E1 dagger plus E2 rho E2 dagger plus E3 rho E3 dagger plus E4 rho E4 dagger. Just need to find E1, E2, E3, and E4. So this is fairly easy. Also, there is a last exercise, which is pretty dumb. I don't know, it just like applies, you need to find the Kraus operators for this double slit coupling that we discussed a couple of exercise sheets before. Okay, I think I held you long enough today. Yeah, so maybe to recap the problems in the exercise sheet, the first problem is about the Bloch Bowler presentation. I think I covered mostly everything there. The second problem is about distinguishing the states. These three states in the table that we discussed, and finding these entries in the table that we discussed. And yeah, the last exercise is about this Kraus operators for the coupling in the double slit experiment. Yeah, also, if you please fill out the Google form that if you haven't still, which was sent to. So this is very informal. Like all the entries are anonymous, and this feedback would really help us to continue with the course. Okay, I think this is all for today. Are there any questions? Okay. Then if there are no questions, thank you very much, and yeah, have a nice end of the week. See you next time.